Hello.
Hi, Oscar.
Can you see me? Just fine. Oh, I see. Is that San Francisco in the background? I
It
was
is.
messing. I was messing around. Lovely to meet you. How do I pronounce your name? Is that Leonie?
Leonie, yeah, that's fine.
Okay, amazing. Very lovely to meet you.
Nice.
I don't know if Julian has already walked you through how this works,
No,
roughly.
no.
Okay. So, would you like me? Julian will probably be joining us in a few minutes, and we'll take over from there. But let me give you a quick introduction. So, what is happening is that we have, in addition to the Zoom call, we also have a YouTube channel, and just to prevent internet strangers from coming on and saying rude things, which has unfortunately happened to some other societies over the years. What we've done is we've restricted the people who can access the Zoom call quite significantly and instead directed them towards the YouTube. So don't be worried if there are like very few people on the Zoom call. I reassure you I looked at the Facebook event and there was something like 50, 60 people said they were interested in the talk, or well, we're going to go to the talk.
That's a lot of people for science talk on a Wednesday
Yeah,
afternoon, exactly, or evening.
yeah, I mean, it fluctuates quite a lot, but we get we get quite a good audience.
Great.
So I see Julian has joined, but how it generally works is there will be a short introduction where we just thank our sponsors and then introduce you and talk about a bit about who you are and maybe even just the title of the talk. And then predominantly it's over to you to give the presentation. Now, the one point of interaction that remains is kind of the questions, right? And often what we found is that people will write those in the chat. And then it's then the whoever is the chair of the talk who will then take those questions, maybe filter them a bit if some of them don't make a lot of sense or reword them or however, and then unmute themselves and speak them aloud. So you don't have to worry about anything technical, just focus on the presentation.
I don't have to worry about the chat. Okay, monitoring that. Great.
Yes, I will just make you co-host, so you should be able to share your screen.
Oh, great. Yeah, let me try that just in a second so we can make sure this all works.
Yes. And then depending on your preference, then Julian, can you hear this? Are you here with us?
Loud and clear.
Excellent. Depending on your preference, Julian can then either take questions during the talk or afterwards if you don't want to be interrupted. That's very up to you.
Afterwards,
if you haven't,
afterwards would probably be my preference, but if there's anything burning in between, I'm also very happy to to interrupt. There's sort of sections in the talk, and that might be a good point to be. Can everyone see the presentation and the proper presentation and not my presenter view?
Yeah.
Yes.
Good, then I can test.
Okay. Okay.
Passed, so great.
I will leave you to Julian while I set up some of the technical stuff with the YouTube thing. Absolutely lovely to see you, and I see we get some people joining.
Exactly.
Lovely.
Hi, Julian.
Hello. Now, just when I'm doing the introduction, I just want to make sure I get the pronunciation of your name right. So how's it pronounced?
Don't worry about it. So it's Leonie Mueck, but if that's hard, don't worry.
Leonie Mueck. Okay.
That's
okay.
Close enough, exactly.
Okay, cool. Oh, anyway.
Yeah, nice to meet you, and just to say thanks again for the invitation. It's really an honor.
Oh well, thank you for it. And actually, well, the one thing that made me really happy is that you advertised it on your LinkedIn profile.
Oh yeah, we also advertised on Twitter. I think our contact person was on it.
Yes. Oh, very nice. Yeah. I mean, I don't follow on Twitter, but On LinkedIn, I follow. So no, that's really nice. Made me happy. So good. We'll start the talk at 5 minutes past, just so we can let some people come in and all that. We already see the chats building up. Should be about
the YouTube thing should now be live, Julian. If you click on the link in the Zoom, there should now be a live link.
What in the wait, where, Oscar, in the chat or in
there should just be on the Zoom, there's a little live on YouTube on on Zoom. Just click on that and you should be able to go to the YouTube link. I'm pretty sure. At least that works on my end. I don't know if this is universal. Otherwise, I'll just send you a link if that's easier.
Could you send a link if that's easier?
Yeah.
It's just because I'm doing it on my iPad and then it's it won't really show up nicely.
Yeah.
Bubble.
2 seconds. I'm sending it on Messenger. Here you go. Here you go.
Ah, beautiful, beautiful time. Beautiful.
Yeah. And I will just send out a very short email reminder to the mailing list that it's starting approximately now, and then I trust you'll handle everything else.
Mm-hmm.
Thank you so much.
Looking forward to it. But in the meantime, Leonie, how has Riverlane been affected by the recent changes and circumstances and all that?
In terms of EU funding, etc.
Well, I mean, I was just asking more on sort of all aspects, really.
Yeah. So a bit, I guess, although we currently don't get that much funding, or we don't get any funding from non-UK government bodies or the EU at the moment, but it obviously prevents us from applying for it now. So that's a bit sucks.
Yes. Yeah.
In short.
well, I mean, it's a nice summary of the situation. It's a nice summary of the situation.
I mean, I should say in the UK, there's a lot of funding available, right, for quantum computing. So we're in quite a lucky situation.
I should just say I have sent the reminder out now, so feel free to start whenever you would like to.
Okay, cool. Let me just go.
I should also say we have about 40 people watching on YouTube at the moment, and that's probably going to increase a bit.
Yeah, and then we got 11 in the chat. I will be taking notes throughout the talk just to see how many people join, because it's always nice to sort of just bundle it all up at the end and then just see how many people we have. It's great. That everything cool. Let's go. Okay, hello, welcome everybody to our final CUPS talk. It has been one of the more peculiar turns, but thank you for everyone who has been joining throughout. It's been a real pleasure, and sadly I won't be speaker liaison officer anymore, so next year you'll be seeing the great work that I've been supporting in the future speaker liaisons. And with that all said, we will get into our talk, but first I would just like to quickly thank our sponsors: Seamless Technology Partnership, TPP, Define, Jane Street, CGG, and Riverlane. And speaking of Riverlane, our speaker knows thing or two about Riverlane, since she is the vice president of the chief product officer at Riverlane, Leonie Mueck, who is giving the talk today on how to turn a quantum computer into a product. And without further ado, I will pass it over to our speaker.
Thank you so much, Julian, and thanks again for the invitation. It's really an honor and a pleasure to be here, and I hope I can give you some glimpse of what the work we're doing at Riverlane on quantum computing and kind of my take on the subject today. I'm going to share my screen now and then double check that it's all working before
Of course.
And perfect. Can you see the actual screen and not the presenter screen?
Yes, full screen. No.
Lovely. So yeah, I want to talk today about how to turn a quantum computer into a product. And what is a product even, or what's important for a good product, right? If you ask product demigod Marty Kagan, one of the people that, was fundamental to the discipline of product management, has written the most well-read books on the topic. A product, it can be, or good product can be summarized in this formula. And now you're all physicists, so I'm sure you find business philosophies written down as formulas a bit weird and potentially even slightly irritating, because like, what's even the units here, right? But anyway, it's a pretty good shorthand for how you can approach defining, testing, and building a product, right? A product is an object, material, or immaterial that makes a good number of users happy by fulfilling a previously unmet need. However, while the user is sort of the center of the product and product thinking, delighting a user will always be constrained by the technology. A teleportation device is a product that probably would find a lot of users, but impossible to make from the technology side of things. And the other constraint that we always have to consider is how the product would be commercialized. What are the business constraints that I'm working under? How much would it cost? And how much would you have to charge? Nowadays, every startup company, Riverlane included, wants to be a product company, right? Because in particular, a software product company, software is really fiendishly hard to build. But once you've built it and you can make lots of users happy, you have high margins. It's very easy to distribute and you can delight a lot of users at the same time. But what does that really, really mean for quantum computers? And so in this talk, I'll attempt to explain and give you a flavor for how this formula is being applied to quantum computers. I'll first speak about potential users of quantum computers, namely computational chemists. And then I'll explain some of the technology constraints that we're currently working under the status of the technology. I'll go back to the users and explain what they might attempt to do with a quantum computer. And finally, I'll briefly touch on the business. What does it currently mean to commercialize quantum computers? What's the ecosystem like, etc. So without further ado, the users, computational chemists. And I want to take you back to my undergrad, which was, so I'm a chemist by training, and I studied in Germany. Germans are very, very proud of having a very thorough, practical, experimental chemistry education. So a lot of that time was spent in the lab during my undergrad. And so this story is about one of the most frustrating experiences I've ever had in the lab. This molecule that you can see here is called lawlimalide. It is a natural product that at some point was conjectured to have, to be potentially an anti-cancer drug. And so it was a big interest from synthetic organic chemistry to be able to synthesize this molecule. And during my undergrad in 2006, I was assigned to a PhD student who was trying to do exactly that. And I was tasked with doing one of the very simple reactions, namely starting with this ring and doing a very simple substitution reaction to get some of these fragments here added to this ring. And it should have been totally bog standard substitution reaction, and it just did not work. It did not work. Something unexpected about the structure or this particular molecule made it impossible. There were maybe steric effects that we didn't quite understand, but who could really tell? So after weeks of experimenting with temperature and reaction time and reactants and solvents, I got a tiny, tiny bit of this desired product. And so my biggest wish from this most frustrating experience from my undergrad was that I wanted to have a giant magnifying glass that would just allow me to look into my flask and see exactly what's going on in it.
Fewer people than the mic doing.
Okay. If there's any questions, please unmute yourself. So after that experience, I actually decided to become a computational chemist rather than an experimental chemist because it was so traumatizing. And in that process, I learned that actually these giant magnifying glasses for chemistry exist. They're called computers, right? Because electrons, the particles that determine chemical reactivity and behavior, are quantum mechanical, and we know how they behave. It's described by the Schrödinger equation. The Schrödinger equation, in fact, predicts the whole periodic system. It predicts everything that might happen in a molecule. Quantum mechanics is an incredibly successful theory, right? It can predict chemical phenomena like the geometry of a molecule, the transition state during a reaction, a spectrum or a crystal structure. Alas, it's not possible to solve the Schrödinger equation by brute force for almost all cases. The famous many-body problem. What messes you up is the electron-electron interaction term here. We can solve it for one electron systems like the hydrogen atoms, and I'm sure lots of you will have done that. So in your quantum mechanics course, but that's sort of it. We can't do many electron systems just straight from this equation. So how computers solve this problem, this is the general idea of how they usually do it. It's called Hartree-Fock theory. It's quite old. It was invented in the late 1920s, but really only took off when we had digital computers because it's really quite complicated to do this by hand. So what we do in Hartree-Fock theory is that we first invoke the Born-Oppenheimer approximation, which says that because electrons move so fast, so much faster than the nuclei of the atoms, nuclei, we can assume the nuclei to be static. And then we write this many electron wave function as a single determinant, a so-called Slater determinant. It's important that it has this form of a determinant because electrons are fermions and you need anti-symmetry. You need the wave function to change sign when you exchange two electrons. You then typically work in a basis set, which is a set of functions that you can combine, so they describe your one electron wave functions well. And these one electron wave functions are typically called orbitals. And then you use a variational method to solve for orbitals that minimize the energy. This is an iterative procedure. In other words, you look at each electron in terms of how it interacts with an average charge of all the other electrons. It's sort of like a mean field theory. And I thought it might be interesting for people from Cambridge to see this to this point that this only took off in the 1950s when we had digital computers. This is quite an early publication that I found where that actually went a bit beyond Hartree-Fock theory, but it was done on the ETSAC, which was one of the first von Neumann architecture computers ever built, and it was built here in Cambridge by Maurice Wilkes and others. So yeah, this is a great example of this sort of theory, this sort of computation, and this sort of way of thinking about chemistry really taking off when we had computers. So there are various approximations and that I make in Hartree-Fock theory, and the most important one is that I just assume that I have one single determinant to represent my wave function. If we consider all the possible states, there are lots of options of how I can distribute my electrons here in my orbitals, right? But I am only considering one of these possibilities, the ground state. But in reality, these sorts of higher excitations, they mix in a bit, right? The actual exact solution is sort of this plus small amounts of excitations. I need to give the electrons more room, if you will, more degrees of freedom, so I can converge towards the correct solution. So if I consider how many possibilities there are of distributing electrons in orbitals, there's an exponential number of possible states. And when we consider all of these states, the solution is called full configuration interaction. And this full configuration interaction then scales exponentially with the system size, but it is in principle the exact solution to the Hartree to this problem. We're making a couple of other approximations like the Born-Oppenheimer approximations, and we're also considering that this is a non-relativistic equation, etc., etc. But let's neglect those for a second, right? So considering all of these possibilities of distributing the electrons in my orbitals gets me to the exact solution, apart from these other approximations that I make. But it comes at a very, very high cost. It scales horribly, and I can only ever calculate very, very small systems. So Hartree-Fock theory isn't always accurate. Full CI is usually not practical. Where did this discipline called theoretical chemistry how did that come about? So what theoretical chemists have been doing in the last 70 years is inventing a whole forest of methods that go beyond Hartree-Fock theory, but that give a better kind of trade-off between computational cost and predictive power. The biggest success story in quantum mechanical method development is probably density functional theory here, which happens to hit a sweet spot between kind of computational scaling and accuracy. In density functional theory, we don't solve the Schrödinger equation directly, we sort of reformulate the problem. We don't work with a wave function, we work with the electron density instead. And then we fit certain empirical parameters. But armed with these sorts of approximations, we can really determine geometries to a pretty good accuracy, like to an accuracy that allows us to, to make some chemical conclusions. We can predict spectra. This happens to be a spectrum from my own thesis, a rotational spectrum. And we can also predict transition states and reaction kinetics. This would have been very, very important in that problem that I had with my lolly-malide natural compound synthesis. But unfortunately, while we've seen so much progress in the last decade, especially with computer power exploding as well, this progress is coming to a halt a bit. And it's not only that, Moore's law is coming to an end and we're not seeing computer power expanding as, increasing as quickly anymore. It's also that it seems like we've exhausted the method development arsenal a bit. Since the invention of DFT and certain versions of DFT, there hasn't been that much progress in really finding good methods that give you a good computational cost predictive power trade-off. So as it stands today, when I go back to my giant, magnifying glass analogy, regular computers, not quantum computers, regular computers are imperfect magnifying glasses of chemistry. And they can either give you a very crisp view of a very, very small part of the reaction, for example, how one solvent molecule behaves, or you can zoom out and show the full picture and simulate all the solvents and all the reactants, but everything is a bit blurry and out of focus. Okay, so enter quantum computers, right? These are these amazing apparatuses that are promising to be a step change in computational chemistry. The hand-wavy explanation for this is that they're quantum systems themselves, so they can represent electrons and molecules with much greater ease than a regular computer. And that is the reason that, while on classical computers, calculating the exact solution to the Schrödinger equation scales exponentially in system size, on a quantum computer, the scaling is linear. So the inner workings of a quantum computer are absolutely fundamentally different from your regular laptop. In your laptop, you have a CPU, and that's your workhorse, and it executes all the programs that you have, and it's filled with these transistors, right? These semiconductor devices that can be on or off, corresponding to a 1 or a 0. And these then form NAND gates, and the NAND gates, they form their whole architecture. Quantum computers, on the other hand, are based on qubits, and qubits are constructed from two-level quantum systems corresponding to the bits of a regular computer. But using advanced experimental techniques, you can also produce linear combinations of these states. Somehow there's a formula missing. Anyway, you can produce these superpositions of these states that are often represented on a sphere, the so-called Bloch sphere. You can see the 0 and the 1, and then it can be any state in between, if you will. Now imagine you have a system of many qubits, let's say m, and each qubit has a coefficient corresponding to the probability of finding the state in 0 or in 1. And this means that there are 2m possibilities of different combinations of zeros and 1 that you need to consider. And fundamentally, this is what gives quantum computers their power. You can consider basically 2 to the m possibilities at once, right? The problem with any quantum system, however, is that in order to extract any information from it, I need to observe it, right? I need to measure it. And this measurement thing often trips you up. So, I'm sure from your quantum mechanics course, you may remember this poor cat, Schrödinger's poor cat, that's dead and alive at the same time before you open the box and measure. And then when you open the box, you know it's definite fate. And the same happens in quantum computers. We are in a state of endless possibilities before we measure, but as soon as we open the box, figuratively speaking, the state collapses into just one of the many possibilities. And that is fundamentally the reason that harnessing the power of quantum computers is actually sort of really, really difficult, because we need to figure out how to extract information without just collapsing everything into a random state. So very, very clever mathematicians and physicists have succeeded, however, in designing algorithms that do exactly that use this wonderful property that quantum computers have of being in so many states at the same time and being able to extract information from it. But this is really, really hard to do. And there are only a finite number of quantum algorithms that give you a so-called quantum speedup, that give you any advantage over classical computers. And not all speedups are made the same. There are speedups, there are algorithms that give you an exponential speedup compared to your classical computer. For example, the famous Shor's algorithm with which you can do prime number factoring. And then also quantum chemical simulations. There are algorithms that give you a square root speedup, for example, Grover search. And then there are specific algorithms that give you, well, we're not quite sure what speedup exactly, it's kind of heuristic. For example, specific optimization algorithms and quantum machine learning. Well, this is really good news for all the quantum chemists then, right? So let me explain a bit more why does quantum chemistry scale so much better on a quantum computer? So we'll go back to your water molecule and the electrons in your orbitals. So let's assume you have m orbitals and n electrons, right? So the way we can represent this wave function now is we don't have to do it by summing up over all the terms that we have and considering all the different ways of distributing these electrons in these orbitals. We can simply prepare this as a superposition of these different types of distributions of electrons and orbitals that we have. And this means that we can encode this type of state in a register of m qubits rather than the 2 to the m qubits that we would need classically. That's pretty amazing. So how do quantum computers look today? There are various different physical implementations of qubits that are in the race to sort of become the transistor of quantum computers. And I currently don't know which one's going to win out. You can ask me about my opinion, but I'll be Switzerland in that regard. I really don't know. And there's great things happening in all of these technologies. So, for example, you can use atoms, neutral atoms, or trapped ions, so charged atoms, and you can make basically these two-level systems out of them that you can then manipulate to be in superpositions, etc. You can use superconducting qubits or superconducting systems. They are mesoscopic systems in which this two-level quantum system that you need is formed by both Einstein condensate of Cooper pairs. These Cooper pairs are the pairs of electrons that are bound together in superconductors. Superconducting and atomic qubits are currently considered the most advanced, although photons are also really, in the race and catching up. There have actually been 2 instances in which quantum computers have outperformed conventional computers at very specific tasks. One is a famous experiment by the Google AI group with 53 qubits working with superconducting qubits. And then there's another one with a very specific task that's a bit different from the quantum computing we're talking here. But anyway, it's called boson sampling, and that was done with photons. But anyway, no matter the specific implementations, qubits are really fickle objects. The slightest contact with the classical world destroys their quantum nature. This is a process dubbed decoherence. And basically, the system loses its ability to be in a superposition of states and simply is flat out and boring and classical. And that obviously destroys any quantum computation that you may have done or that may be in process. Sorry. So you may have asked yourself, actually looking at these pictures of these different labs with different types of quantum computers, what are all those boxes in those labs doing there? What do I need all of that for? And the answer is that this is basically the life support of a qubit, the life support system of a qubit that keeps it in from decohering, right? We need complicated control system consisting of analog control units like lasers and waveform generators. Then we have fast programmable elements like FPGAs. And then we also have lab computers, and all of these have to work together to keep the quantum computer from decohering, or the qubits from decohering, extending the lifetimes of the qubits so that we can actually run long calculations on them. So, and even further than that, we actually need a process called quantum error correction in the long run, so we can extend the lifetime of the qubits. So in quantum error correction, what happens is that the same information gets encoded in qubits multiple times, redundantly, so that you can then check whether any of these qubits have decohered and then correct the error. Quantum mechanics makes this error monitoring really, really hard, rather complicated, again, because if you measure, you destroy your state. So how do you look up whether an error occurred if then everything, just gets destroyed if you look it up? So you need very, very clever layouts. Here's an example layout of how you do this. These are called codes, essentially. This is a very specific code called a Steen code. And then you need tons of ancillary qubits that allow you to then measure whether any of these qubits here has decohered. And this is really quite difficult to do, especially if you have a computation running and you need to check during your computation whether anything is decohered. So, and the result of that is that you need thousands and thousands of qubits, of physical qubits, to represent one logical qubit, right? So what you then do is you have your data qubits and you have your ancillary qubits, and you imagine there's some noise. you do something called a syndrome generation. Then you do a syndrome measurement, you measure your syndrome, you decode this error, so you actually check whether there was an error, and then you do the error correction if this error occurred, and then you correct the data qubit. And all of this has to happen incredibly fast. In microseconds for atomic qubits and nanoseconds for superconducting qubits. In superconducting qubits, you have the additional problem that these superconductors have to be kept at very, very, very low temperatures. You have to do it in the fridge. This is all really, really, really quite difficult. So your heart, I'm sure, must be sinking right now. You know, if we need thousands of qubits to enable error correction and have 53 sort of working qubits right now in this Google AI experiment. So how the hell are we ever going to use a quantum computer as like a true magnifying glass for chemistry? This just all sounds like a pipe dream. So while constructing a fully error-corrected quantum computer is really, really difficult, and the billion-dollar task that the industry is facing today, right? That's definitely what we're aiming at. So the thing that makes me sort of optimistic that we will get there eventually is that there's sort of like a quantum Moore's law. So in the last decade, we've seen a yearly doubling of quantum computing power, as measured by how many qubits can be built, combined with how noisy they are. And there's another piece of good news. We won't necessarily need a fully error-corrected quantum computer to do useful things. We can maybe use so-called noisy intermediate scale quantum, or NISQ devices, NISQ with a Q. And those are already under construction. So in chemistry, there are two main algorithms which you can use to compute chemical properties. And both of them can be used to solve the Schrödinger equation. And one of them is NISQ and one of them isn't. So let me briefly take you through these two algorithms. So the first is called quantum phase estimation, and that was also historically invented first. And in this algorithm, we directly encode the physical description of the system into the quantum computer, and then perform a series of manipulations to extract information about the energy as we measure. Quantum phase estimation is based on the quantum Fourier transform. This is the quantum analog of the fast Fourier transform. And this is actually also the sort of subroutine that makes factoring integers so fast. And this quantum Fourier transform can be used to estimate the phase of a state. And that's equivalent to solving an eigenvalue equation, basically, here for the energy. In other words, it can be exploited to calculate the spectrum of a Hamiltonian. So to run this algorithm, you need two types of qubits. Ones in which you load the state you want to study, and another set on which you then eventually write the state of the binary. And you generally don't know what the spectrum of the Hamiltonian is, so you have to guess a little, because your initial input needs some overlap with your actual answer. And then you prepare superposition of all of these states, perform this quantum Fourier transform. You get an entangled state between your original state and the energies of each component, and then you measure these qubits. By the measurement postulate of quantum mechanics, this gives you kind of a spectral energy as a readout. And there you go. This is really the best algorithm for determining the spectrum of the Hamiltonian, but it requires a very, very long quantum circuit. So this thing that I just call here quantum Fourier transform, this is actually a lot of operations where you pick up bits of the phase. So it will be very, very hard to implement this in so-called NISQ devices, because the qubits we currently have, they are not long-lived enough. We really need error-corrected qubits to do this properly. So there are, however, algorithms that are really quite promising for these near-term machines. And one of these is the variational quantum Eigensolver. And this is a hybrid algorithm in which you basically just outsource the hardest bit, the bit that's hardest on a conventional computer, to the quantum computer. So this algorithm is based on the variational principle. in the same way that, the Hartree-Fock theory is based on the variational principle. And we choose a reference state, for example, the Hartree-Fock state, and this Hartree-Fock state has a set of parameters, and then we prepare it on the quantum computer. We run a circuit to prepare the state that depends on these parameters. We measure. We do this a couple of times because all of this is a bit probabilistic, and we want to get to a certain accuracy. Then we evaluate the energy by just calculating this solving the eigenvalue equation, and then we put the result back, and we do this on the classical computer. Then we put the result back, choose a new set of these parameters theta, and do the same thing again. So this is quite a good algorithm to use on your TIM devices, because the quantum resources that you use are only to prepare the state and then measure the energy. So it does not need exceedingly long coherence times. The main advantage, obviously, to classical systems is that these quantum registers can store exponentially more states compared to classical memory, right? So in this variational quantum eigensolver, compared to the quantum phase estimation, we have substituted a long series of manipulations for shorter series of measurement performed many times. And we can use a device with a relatively short qubit lifetime to perform a chemistry calculation. So in theory, both the variational quantum eigensolver and quantum phase estimation have been claimed to deliver exponential quantum speedup compared to conventional quantum chemistry. But for the variational quantum eigensolver, this whole thing is a bit tricky to estimate, because you don't only have this quantum routine, you also have this classical optimizer, and we don't really know what the errors are in the system. How many times do I have to prepare and measure, depending on how noisy the system is, how far off the actual solution do we start, and how will our classical optimizer that we use here perform. So this is actually quite hard to estimate how exactly this will perform on an actual quantum device. And just to say that there are various results on how to combine the merits of quantum phase estimation with the variational quantum eigensolver. So we can use, qubit lifetimes, coherence times, optimally as they get longer. Okay, after this bird's eye view of where the tech is in quantum computing, let me go back to the user, the chemist, and explain how they might make use of quantum computers, right? So if I go back to my horrible, frustrating experience of Lolly Malide, how would I have tried to solve this on a conventional computer? I would have likely turn to density functional theory, which I mentioned before, which is kind of the workhorse of computational chemistry today, right? Density functional theory provides sufficient geometries for organic molecules, sufficiently accurate geometries for organic molecules, so I can get some insights into steric effects and participating solvent molecules. I drew some water here as solvent molecules. I don't think I used water for Lolly Malide. I think I used some organic solvent, but you get the principle. So in this magnifying glass analogy that I used at the beginning, so this density functional theory is a method that gives you sort of a medium-wide view and just about acceptable focus, right? You get a pretty good idea as to what happens in your chemical system if you know what you're looking for, and if you know what the approximations exactly are that you're making, and you can get a good intuition, good feel for it, right? However, and so this would have got me good transition states and geometries. So probably a pretty good idea about the mechanism. However, in any reaction, chemical reaction, something that is quite important is bond breaking and bond making, right? I stretch bonds and then, molecules fall apart or they form. And in this bond breaking and bond making process, what happens is that I arrive at states that are very, very close in energy, or degenerate states, or quasi-degenerate states. And these are really quite hard to tackle on a classical computer. DFT absolutely completely fails. So the types of methods I would have likely turned to on a conventional computer are multi-configurational SCF. So this is kind of like a way of extending Hartree-Fock theory by considering two Slater determinants and optimizing the orbitals for both separately. Or I would have used so-called couple cluster theory, which is a bit the gold standard in terms of accuracy for quantum computing, for regular computing, sorry. So couple cluster theory is usually used to obtain really quantitatively accurate results for geometries or reaction energies, but I can't use it beyond, say, 30 atoms or so. So to look at this whole Lawley-Malide molecule couple cluster theory would not have been practical, because it would have not been possible to calculate this on a conventional computer. This would have been too expensive. So from that analysis, what I think quantum computers will sort of catch up with first, right, in the NISQ era. So they will have to calculate. They will have to only be able to calculate relatively small molecules. So these small quantum computers need to be able to compete with relatively highly accurate methods such as couple cluster theory. And the first hurdle to clear is the accurate description of small molecules and reactions, for which even couple cluster theory fails. For example, these multi-reference methods. Nowadays, people are fairly confident that with a couple of hundred qubits with like really decent lifetimes, like really good coherence times, we could potentially beat a conventional quantum chemistry computation. But this is still an open question. But now you have to consider what happens if the quantum version of Moore's law holds, right? So imagine you can do very small molecules to a very high accuracy. You have all the methods, you have good qubit lifetimes, etc. So and then quantum computing power doubles every year, right? If that still holds, that means that within 3 years, we will have increased our computing power like 16-fold, and we will be able to kind of take our magnifying glass that's super, super crisp, right, for a small region, and just extend it and expand it. So zoom out, and the view that we have of our molecule and our reaction will still be super crisp. We will have the ability to calculate large systems, large chemical systems to a very, very high accuracy. And then it won't take long until we have enough qubits to properly do error correction and run really long computations. So let me explain how this might play out in a very, very specific area of where computational chemistry today plays a role in industry, in drug discovery. And obviously this is speculation because we don't really know how this is going to play out, but still, let me make the case. In drug discovery, you're usually interested in how a specific drug interacts with an enzyme, right? That's what you want to look at. So here we have an enzyme. It's a metallobeta-lactamase. And metallobeta-lactamase are pretty evil enzymes because they destroy carbaponyms, which are antibiotics of last resort. So this beta-lactamase, the one that I show here, has a zinc atom. That's the gray blob that you see here in the middle. And so the big question here, the big scientific question that we need to answer in order to understand how we could keep beta-lactamases from destroying these carbaponyms, is what is exactly the mechanism as to how these carbaponyms get destroyed. So when answering this question with conventional methods, you have to fight with a lot of computational challenges that are very hard, namely bond breaking and bond making, because we're talking about a mechanism. But then we also have a metalloenzyme here. So we have a metal in the center, and this metal has anything with kind of a transition metal or a metal inside has, again, these degenerate states. So lots of states that are very close in energy. So many of the traditional methods that you would use, they break down. So enzymes are really, really rather big molecules. So the way you would treat them on a classical computer is that you would splice them up into regions, as I kind of have shown here. And then you would only treat the most important region with a very, very highly accurate method, and sort of gradually get less accurate in terms of your methods as you go out and go away from the center. This is called embedding generally. And what you can imagine is that once quantum computers are able to do so, that you will simply be able to calculate the most important region on the quantum computer. Then you go out a tiny bit, right, to a less important region. You would calculate that with a fairly high accurate method on a classical computer, and so on and so forth. And as quantum computers increase in size and quality, you will be able to expand this region in the middle, right? Okay. Let me now come to the very last bit of my talk, which is what's the landscape like at the moment? What are we doing in terms of commercializing quantum computers? So much wiser people than me and much better informed people than me have thought about this in depth, including the Boston Consulting Group, and in a now almost infamous report. They came up with some numbers as to what they think the quantum computing market will be worth when. And so they predict that in the NISQ era, so in the next 3 to 5 years-ish, the quantum computing market will be worth $500 million for the materials industry annually, and $600 million in the pharma industry. And this sounds like a lot, right? But then consider what they are predicting for fault-tolerant quantum computing. $55 billion for the materials industry, and $75 billion annually for the pharma industry. So this is really the opportunity that complex quantum computing brings. And even if these numbers turn out to be a bit too high, which they potentially will, these are huge opportunities that we're looking at. So this is no surprise then that the quantum ecosystem, the quantum computing ecosystem, is thriving. Since 2012, there's been $1.5 billion in private investment into quantum tech startups. The number of hardware startups has been exploding, the number of quantum computing hardware startups in the last couple of years. This is kind of a little map that an online publication called Sifted made of quantum computing and quantum tech startups in Europe. And you can see it's quite crowded. Riverlane's over there. The UK is doing very well, but there's all sorts of activity going on in Europe. So given that sort of funding situation, given the state of the technology, given that we have that there's such a great use case for quantum computers in quantum chemistry, I am fairly confident that by sort of 2050 or so, an organic chemistry student will be able to use a quantum computer to get more than just blurry insights into what their reaction is and why it is not working. And I, in fact, think that the advent of quantum computers could make computational chemistry so central to gaining chemical understanding that it will be the first topic that chemistry students learn, rather than one that comes like way later in their education or nothing at all. And of course, chemical rules and knowledge will be by no means obsolete. We still must know how to ask the right questions and devise sensible hypotheses, etc. But testing them will be much less laborious and painful once we have quantum computers. If you'll indulge me for 5 more minutes, I'll talk briefly about what Riverlane's role is in this whole quantum ecosystem and in this whole sort of space that I described for you. So one thing we do at Riverlane is we work on quantum chemistry algorithms, because quantum hardware increases will not happen in a vacuum. Through better software and algorithms, we can understand how we can use available hardware more efficiently. And in this figure, you can sort of see how through software and algorithm developments, the size of a necessary quantum computer to do something useful has decreased just by itself without any hardware development, right? And software development and algorithm development is usually cheaper than hardware development, so that's a pretty good deal. And so we work on various aspects of this, better methods to prepare chemically relevant states, methods to measure the energy more efficiently, new families of chemically relevant states, methods to use VQE to measure spectrum of excited states, and many other things. The other thing we're working on is sort of the question of how we then efficiently run algorithms on quantum computers. This picture that I showed you, I think I showed you this before, with this network of different types of control elements, that's actually part of how we think about writing a program onto this complicated life support system that we have in quantum computers. And this system that we're working on is called Deltaflow. Deltaflow lets you write programs directly onto this control system, and via a hardware abstraction layer, you can make these very, very efficiently implemented algorithms portable across different types of qubit technology. And we're working on Deltaflow with almost all hardware providers in the UK. And this consortium also includes ARM as well as the National Physical Laboratory. We're very proud to be working with all of these partners. And last but not least, we have a couple of open jobs at Riverlane. We're currently looking for a DevOps and test engineer, as well as a senior software tech lead. But we're also open to applications from other people, in particular, if you're interested in writing software, if you're interested in turning kind of research into software, contact us if you want to work for us. You can find us at team@riverlane.com. And now thank you again for the invitation, and thanks everyone for your attention. I hope I could give you a bit of a flavor of what I think the quantum future holds, and I'm open to any questions.
Thank you, Leonie. That was such a brilliant talk. Learned so much. Really interesting stuff. I really love the story you painted there with your time as a university student and the frustration you have at Liliamide. I could see why you would want to make it because I googled and the price is some ridiculous amount for a gram. So I could see why there's an incentive to make it. So I think now we'll get into some questions. And obviously you mentioned the funny comment of you want to be Switzerland in the technology department. So I'm gonna question you a bit more on that. Do you have any, what do you think are the kind of the key features? What do you have any opinions on the topics of what technology and all that?
I really don't. I see so many good ideas that are currently being explored, in particular regarding kind of scalability, right? This is the big the big question. I don't only need 2 to 5 atoms that I need to manipulate, but thousands, and how do I do this? And there are many great engineering ideas that are coming up, right? So yeah, I really couldn't tell.
Neutral indeed. On the comparisons chart with DFT and exact solution to the Schrödinger equation, why is the exact solution placed at lower computational cost?
Yes, because this was a mistake. I'm sorry, this should have been the other way around. I'm realizing now. Please apologize. Exactly. So let me show the slide again and then clarify this for everyone. There we go. So here you have sort of the highest computational cost is here, and the lowest computational cost is here.
Yes, yeah. Cool. So clean that one up. Little question from Oscar. From the sort of from the understanding we have and sort of kind of environment, most of the business cases for quantum computing is still a little way off. Like we have sort of 50 qubits, but a lot of time you need quite a few qubits. So how come so many companies are entering the industry so early then?
Mm-hmm. Well, I mean, of course, there is a huge advantage to being an early mover, right, in this space that is so incredibly promising, and sort of gaining a lot of IP, right, gaining a lot of experience. Well, we're in a very lucky situation, at least Riverlane is, that we have investors that think long term, right? They think about what might happen in 10 years time rather than 2 years time or 3 years time. But obviously quantum computing isn't something that is going to take off like super soon. It's something for the patient who's willing to solve a lot of very difficult technical problems. The business case I don't think it's 20 years away. I think we will see some early use cases much sooner, and as soon as we have the sort of general quantum advantage, even for very specific use cases, there is a business case for it.
Okay. Yeah. Well, awesome. Thank you. Just another little question. Obviously, sort of on that, quantum computing is really kind of the sort of becoming technology in the future. And as you said, that might be the first thing you learn as an undergrad. So what do you think currently is the best way to sort of get into the industry, learn about the industry? Any books you recommend or sort of things to play around with?
Yeah, sure. So one thing that I want to mention here, and sorry for the ruthless advertising, is we have a summer internship program for undergrads. Unfortunately, it just closed, but next year there will be a call for it again. So please watch out for that. But we're not the only ones who have that. There are lots of other companies that have these sorts of internship programs. So that's one good way. I should say that one company that has probably done more than any other for sort of the education, especially at the undergrad level about quantum computing, is IBM. They have really amazing tools online with which you can learn quantum computing. So that's something that anyone who's interested could look into. There's the absolute classic in terms of learning about quantum computing is the Nielsen-Schwang, and because I looked up some quantum phase estimation stuff, I have it here. I can.
Oh, wait.
Exactly. You might have it there too, Julian. Oh yeah, great.
Brilliant.
And there's great resources online, especially from the last year as many conferences moved online. Many of the talks are still on YouTube. I vividly remember that there was this amazing tutorial by Naomi Nickerson from PsyQuantum about quantum error correction just recently, and it's just on YouTube. And exactly, it's pretty easy to find. Exactly.
Quantum, no, Naomi. Yes. Oh yeah. Actually, I was just looking up PsyQuantum today, and they're very pro photonics. Actually, they're extremely pro photonics. Like this is the only way. So yeah. So I mean, that's just interesting to show like how much the contrast are in like people are so for this technology and so not. But another question we have from YouTube. What kind of research is being done on reducing qubit requirements for the VQE?
Yeah, so there's various ways of which you can look at, or various kind of bottlenecks that you can look at tuning, right? One is the specific ansatz that you're using that you then feed into your quantum computer. So this is you can, for example, find hardware efficient ansätze that reduce qubit count. Then another thing that people are looking at is, for example, how to make this measurement more efficient. So something you can do is, for example, collect many terms and do measurement more efficiently. That doesn't really reduce your qubit count, but it does reduce kind of your resource requirement that you need. Another very active area of research is how you can use symmetry to reduce, again, qubit count. So these are just some examples, but it's a very, very active research area. So I'm sure I missed some things that are currently being done.
Fair enough. One after. Is there any error functions in the Steam code, Sean code?
I'm not sure I understand the question. If the person on YouTube might want to clarify, I tried.
There's only error function in the Steam code. Yeah, I'm not quite sure what they're getting at. I mean, maybe they're just wanting a little bit of clarification on how the sort of scheme works, but that's probably a bit of a long question itself.
And that's a long, so it's not really an error function, right? It's a way of defining how you can basically encode redundancies in a clever way, so you can then find out whether you have an error without destroying it, without destroying your quantum state.
Yeah. I mean, from what I was looking at, it's kind of similar to quantum Hamming codes, sort of what it looks like. But anyway, that it requires a Google. Any other questions at the moment? Anything as such?
I'm just going to unmute myself if that's okay, because I am not a fast typer. If that's okay. A super interesting talk. It was very, very, very intriguing to hear an entirely different perspective. Have you tried implementing some of the novel algorithms you've developed at Riverlane on NISC devices? And if so...
We have very good collaborators in Oxford, and we're actually currently doing exactly that. Yeah.
Okay. What's kind of been your experience? What's currently the bottleneck, so to speak, in terms of getting useful or interesting results?
Well, it depends on how you define useful or interesting. The quantum computer that we're currently working with is the one at the Oxford University Trapped Ion Group. That's the one we're collaborating most closely with at the moment, and it's very small. So in terms of interesting things for chemistry, that's currently a bit limited in terms of that specific type of work that we're doing. But what we're trying to do there is sort of seeing how we can implement these algorithms more efficiently. So how we can use this, I showed you that there's various control elements, right? And so the way that you can use kind of your qubit lifetime more efficiently is by by making use of local control, by very kind of fast control that reacts to what's happening in your qubits. And that's basically the kind of the line of research that we're doing there. That's overcoming a very specific type of bottleneck, obviously.
Okay. That's really interesting. Thank you very much. Just seconds. Let me just get another one from YouTube.
I got it up on Oscar.
Okay, amazing.
Is the work you do at Riverlane mainly on the business technology or the theoretical research?
So I'm not sure if this relates to me personally or Riverlane generally. Me personally, I am I don't have a technical role at Riverlane, so I'm chief product officer. My main job is to basically sort of sit at this intersection of the technology, the business, and the user, right? And see how we can make quantum computing work in this sort of triangle of requirements. So my job is non-technical, but I have to understand the tech really quite well to be able to, to sit there in the middle of it all. So that's my job. Just to say, I love product management as a discipline. It's really great because it has a technical aspect to it, and but it is a bit of a generalist kind of job. So for me, it's just the right thing. I'm not sure if that many people here on this call, especially if they're undergrads, have heard of this discipline. There's lots of resources out there where you can find out more. So just to say, if you're curious, that may be something to look into for what you want to do after your undergrad. It's really great. It's a great discipline, or great thing to do. Generally at Riverlane, mostly what we do is actually not what I do. It's mostly sort of engineering and research. I would classify those activities. So some of it is really just blue sky research, very much similar to what you would do at a university, and some of it is engineering because, well, we want to build this system called Deltaflow, right? And we want to deploy it, and it should be production level code. So there's quite a big kind of software and system on chip engineering effort at Riverlane.
Fair enough. Interesting. Just a bit more of a personal question. So you said that you got into quantum computing mainly because the frustration you had at chemistry undergrad. But how did you go into be a chemistry undergrad, or what are like some key moments and like wanting to go into science and all that for you?
As a chemistry undergrad, before I even chose chemistry, or?
Well. I mean, I'm just wondering, like, what sort of things, like, really, like that you really liked in chemistry, and like why you chose to do chemistry and all that. And
well, when I was in school in Germany, I knew I wanted to do a science, but I wasn't quite sure which one. And chemistry seemed like a very good compromise because you could sort of branch more into biology or more into physics. And I ended up branching more into physics, I guess, because I then did theoretical chemistry for my PhD, and the very, very theoretical end of chemistry, exactly. So yes, but this Lolly Malide experience was definitely quite defining in making me choose theoretical chemistry.
yeah, I can imagine. Other questions. Now, do you see? No, okay. So I guess this question is requiring you to be a non-Swiss, as they say. Do you see a future in photonic devices? For example, implementing the QFT in the near future, for general quantum computers, or do you think that's more kind of 50 years or so?
Yeah, I'm not quite sure I follow the question completely, but I mean, photonic devices, the ones that are currently outperforming traditional computers, right? They're a bit more like analog devices. They're not like general purpose devices. So I assume the question's about that. And yeah, that is a very distinct possibility. It's been shown that these sorts of sort of analogish devices can do very specific things, like, for example, calculate these Frank-Condon factors, like specific spectroscopy problems, very, very quickly, and can be used for that. And that's definitely a very, very interesting area of research. I wouldn't want to fathom a guess as to how far this all is away, I'm afraid.
That's fair enough. Yeah. Oh, Frank-Condon factors. Yeah, I remember. Another question. So in your talk, you mainly were saying about the quantum chemistry and some theoretical chemistry side, but do you know of any other sort of business applications? Because there's, work in quantum cryptography, maybe even like stock picking in finance. I've seen some people who have been, thinking about. So what do you think about those areas of research? And you think they're soon, or they're a bit further away? Do you think there's a lot of hype around it, or?
Yeah, I certainly believe that the first commercially relevant application area that we will see is in quantum chemistry, for all the reasons that I said. There are sort of NISQ era algorithms for optimization. One of them is called quantum QAOA, quantum approximate optimization algorithm. So algorithms that sort of allow you to have kind of low depth circuits and algorithms that could potentially be done on a NISQ device. However, the problem is, if you want to do optimization, usually what you're interested in is big data sets, right? Lots of data. Rather than, small cases. So in order to, consider big data on or like many data points on quantum computers, again, you will need bigger quantum computers. So, I mean, hand wavily, that is sort of the reason why I think chemistry will be earlier, because in chemistry you really have quite small problems that are really, really hard to do on quantum computers, and in particular sort of multi-reference cases where you have degeneracies.
Fair enough. Actually, I guess one thing on that, do you think currently there's a bit of overhype in the quantum computers? Because I know some people are like, oh, quantum computers, they're gonna change the world, we're gonna live on the moon and stuff like that.
Yeah, I mean, I guess I don't want to shoot myself in the foot here, right?
True. But I do, I do realize that in saying the question. But do you think, let's put it this way.
It's fine. I can answer. So obviously, we need to be very honest as a community as to what quantum computers can and cannot do. And we also need to be honest as to how difficult, right, the technical challenges are that we need to solve for them to do anything useful. While I think they're really going to change the world eventually, it's a bit off, and we need to, we as a community need to be honest. And yes, probably there is a bit too much, hype, generally speaking. But obviously we're sort of benefiting from it.
True.
So I shouldn't complain.
Good answer. I mean, I can't imagine that's going to particularly affect your share prices. So, that's all good.
Definitely have one, but yeah.
Any questions on YouTube? Got all those. Those on YouTube as well. Cool. What else do we have? What's some of the major questions? Do you think, like, how realistic is it that you think the quantum Moore's law will sort of hold up? Do you think actually we might exceed it in the future, or we might sort of fall behind, or?
That's a very good question. I actually think that we might accelerate. And that is actually due to a certain extent, to the hype, to the money that is pouring into quantum computing, to the quantum computing space, right? There's lots of money, there's lots of great ideas. And now there's also sort of professional grade engineering. For a long time, it was physicists in the lab, working on the fundamental questions. And now it's armies and armies of engineers. And we're seeing sort of that inflection point at the moment, that it, is becoming more of an engineering activity. And that is not to belittle any of the problems. They're still huge, right? The technological challenges. But so given that, I have high hopes. So I would be very disappointed if it didn't accelerate.
Yeah, fair enough. I guess just a little bit more of a personal question, but what would you say is like your sort of like, I guess your favorite quantum algorithm that there is, just the kind of one stop sort of thing?
Oh gosh, my favorite quantum algorithm. I mean, the quantum Fourier transform is pretty cool.
Who doesn't love a good Fourier transform?
Exactly. Exactly. Because it's in so many, it's a subroutine, right, or sub algorithm to so many other algorithms that are important. I guess that would be a slightly diplomatic answer.
Diplomatic indeed. Yeah. Fair enough. Definitely exhausted my mind of all the questions that I had to ask. Oscar, do you have any more questions?
I'll go back on. Hello. I've somehow managed to place myself in the States via Zoom backgrounds, but I am still in the UK.
At least you're not a kitten, so that's good.
What, sorry?
At least you're not a kitten.
This is true. That would be very embarrassing. No, absolutely lovely. Thank you so much. I guess kind of I don't have any big questions for you. I have maybe some personal like quantum computing device questions I could ask you, but I don't know if those are necessarily of general interest to the audience. So perhaps what we'll do is we'll turn off the YouTube stream, and if you're still willing to stay maybe 5 or so minutes afterwards, maybe I could ask them then.
Sure. Yeah, of course. If I can answer, I'll try my best.
Okay, thank you so much. Then I'll turn off the YouTube live stream. Goodbye to everyone on YouTube. Thank you so much for joining us.
Yeah, thank you.
We will see you all next term. Oh, well, actually not next term, next year.
Next year, Oscar. Oh.
Yes, this is true. Shit, this is the last one.
I know, it's emotional.
It's almost emotional. I should say, I think we peaked at around 80 people in total attending this talk, and then it went down a bit near the questions. I think we're still on about, so it's gone down very, very rapidly right around now, but it's currently